Chapter 13, exponential and logarithmic functions. Section 13.1, exponential functions. And their graphs. Okay, so first let's recall a few things. Power functions. So a power function is just some variable to some power, let's say to the power 3. And so we have some variable base. An exponential function is where the variable is in the exponent rather than in the base. And so suppose we have some fixed base, let's say 3, and we raise it to the power x. So that would be called an exponential function. That's an example. Okay, so in general, an exponential function has some base, and suppose that my base here is greater than 0 and not equal to 1. The reason that we want to restrict our bases to be such that the base is greater than 0 is, well, if the base is less than 0, then you can have, let's say, x equaling some negative number, say or negative uh, a half or something, or just let's just say 1/2. If you have a negative number to an exponent of 1/2, a negative 1, let's say, base to a exponent of 1/2, then it's going to be an imaginary number. And so you do not want negative bases, because if you have a negative basis, then for a whole bunch of these values, you'll have a complex, an output that's complex. And you want this to be a real valued function. If the base were equal to 0, well, you have 0 to a exponent, let's say a non-zero exponent, then that's always going to be a value of 0. And that's not a very interesting function. It won't be a injective function. So similarly, if I have a base of 1, well, 1 to any power is just 1. So again, that's not going to be an injective function. So I want to restrict my bases to be such that the base is greater than 0 and not equal to 1. Then an exponential function is a function of the form b to the power x. Well, let's look at the graph of b to the power x. If my base is greater than 1, then the graph will look something like this. It'll always be increasing. It'll be concave up. Meaning that it's increasing at an increasing rate. It'll have no vertical asymptote. So it doesn't approach some fixed value. And it will have a horizontal asymptote. The horizontal asymptote will just be y equals 0. So it approaches the x-axis. And this is, well, as x approaches, for x being very, very tiny, very negative. It has no x-intercept. It never actually touches the x-axis. It gets closer and closer to the x-axis. It actually never touches it. It has a y-intercept. The y-intercept is 1. Similarly, let's look at the graph of y equal b to the x, and suppose that b is between 0 and 1. Then it looks something like this. And so in this case, it's always decreasing. You can see it's always going down, but it's still concave up. It's still getting a larger and larger values. It has no vertical asymptote. And the horizontal asymptote is again just y equals 0. And this is as x gets very, very large. Has no x-intercept. It never crosses the x-axis. And the y-intercept is again at 1. Okay, so in general, that's what the graphs look like. Let's do some examples. Let's say on page 543. Let's do problem number 1. In exercises 1 through 28, sketch a graph of the function, give the coordinates of the y-intercept of each function, and the equation of the asymptote. So f of x equals 3 to the x. Let's sketch a graph of this. So when x is -2, we're at 1/9. -1, we're at 1/3. 0, we're at 1. 1, we're at 3. 2, we're at 9, etc. And so it looks something like this, the graph. The y-intercept is when x is 0, y is 1. The asymptote is just y equals 0. It approaches the x-axis for values of x approaching -infinity. Let me do problem number 3. F of x equaling 1/5 x. Let's sketch the graph of this. At -1, it's 5. At 0, it's 1. At 1, it's 1/5. Yeah, okay. So this is a graph of y equaling 1/5 to the power x. At 2, it's 1/25, etc. The asymptote is just y equals 0, and the y-intercept is at 0, 1. Let me do problem number 5. F of x equaling 3/5 x. Well, again, it's less than 1, the base, and so the graph will look something like this. So it should look something like this. So y equals 3/5 to the x. At -2 is 25/9. -1 will be 5/3. At 0, it's 1. At 1, it's 3/5. At 2, it's 9/25. It approaches 0 as x goes to infinity. So y equaling 0 is their asymptote. 7. F of x equals 2 to the 2x, which is actually the same as f of x equaling 4 to the x, since 2 squared is 4. So the graph will look something like this. At 0, it's 1. And as x goes to -infinity, it approaches 0. At 1, it's 2 squared, which is 4. At 2, it's 2 times 2 is 4. 2 to the 4th, 16. Let's do problem number 9. F of x equals 3 to the x over 3. Oh, another way of thinking of this, of course, is to look at the sketch of the graph y equaling 2 to the x, and then just compress it by a factor of 2. So it looks a little steeper. We can sketch a graph of this. Again, it looks like the graph of y equaling 3 to the x. But then we have to stretch it. We have to go by a factor of 3, stretch the y-axis by the x-axis, sorry, by a factor of 3. So it should look something like this. You're only stretching the x-axis, so this doesn't change. The y-intercept is at 0, 1, and the asymptote is just the x-axis, y equaling 0. 11. F of x equaling 3 to the power x plus 3. So it's going to look like the graph of y equaling 3 to the x, but we're going to translate it. Since we're adding 3 to the x, we'll translate it in the negative x direction to the left by 3. So it should be 1 here. Okay, so it'll look, so it looks like the sketch of y equaling 3 to the x, except we're going to move it over 3. So it's going to go up. No matter what I do, it's going to go up pretty high and fast. I'll try to make it intersect. Okay, so there. um, so this is the graph of y equaling 3 to the x plus 3. When x is 0, 0 plus 3 is 3. 3 cubed is 27. So this is intersecting at 27. 0, 27, sorry. And, well, the asymptote is just, again, the x-axis, y equals 0. 13. F of x is equal to 2 to the x plus 1. Okay, so again, this is the same as the graph of y equaling 2 to the x, but I'm going to add 1, so I'll go over 1 over. I'll move 1 unit to the left. And so it should look something like this. And so this is the graph of y equaling 2 to the x plus 1. And so the horizontal asymptote is still y equals 0. The y-intercept when x is 0, y is, well, 0 plus 1 is 1, 2 to the 1 is 2. Let's do 15. F of x equals 2 to the 2x minus 2. So again, this looks like the sketch of the graph y equal 2 to the x. However, we're going to be stretching the x-axis. Oops. Compressing the x-axis by a factor of 2 and shifting this over 1. And so let's do that. So let's shift over 1, compress it. Okay. And so the sketch should look something like that. So this is y equaling 2 to the 2x minus 2. So again, the asymptote is y equals 0. And this intersects at when x is 0. 2 times 0 is 0. 0 minus 2 is negative 2. 2 to the negative 2 is 1/4. Okay. Let's do problem 17. F of x equals 4 plus 4 to the x. So this is going to be a translation. We're going to move, this will look like a translation of 4 to the x. So 4 to the x looks like this. And now we're going to move it 4 up. So 1, 2, 3, 4. And so 4 to the x looks something like, so this is the graph of y equaling 4 plus 4 to the x. Well, we moved up we translated this up by 4, so the asymptote is actually y equaling 4. The y-intercept, when x is 0, 4 to the 0 is 1, plus 4 is 5. 19. F of x equals 3 to the x minus 1 plus 2. Okay, so we're going to sketch the graph of y equaling 3 to the x. And so this is the graph y equaling 3 to the x. Then we're going to shift it to the right 1 and then move it up by 2. And so let's sketch the graph of y equal 3 to the x, move it 1 over. And so this is the graph of y equaling 3 to the x minus 1 plus 2. Okay, so as x goes to negative infinity, y approaches 2, so the asymptote is y equals 2. When x is 0, y is, well, 0 minus 1 is negative 1. 3 to the negative 1 is 1/3. Plus 2 is 2 1/3. Okay. And that's the y-intercept. 21. F of x equals 1/2 to the x plus 4. So this looks like the graph of y equaling 1/2 x, which is the same as x 2 to the negative x. So this would be the graph of 2 to the x, and then we reflect about the y-axis. So it looks something like this. And then we translate it up by 4. So it looks something like so y equaling 1/2 to the x plus 2. And so as y goes to positive infinity, as x goes to positive infinity, y approaches 4. When x is 0, 1/2 to 0 is 1 plus 4 is 5. And so the y-intercept is at 0, 5, 23. F of x equals 1 plus 2 to the x over 2. So we look at the graph of y equaling 2 to the x. We stretch the x-axis by a factor of 2, and so it's going to be a little wider. And then we translate it up in the y direction by 1, so it's going to look something like the following. Exaggerating a little bit, but and so y equals should grow a little faster than that. Okay. And so this is a graph of y equaling 1 plus 2x over 2. So the y, so the intercept, the asymptote is y equal 1. As x goes to negative infinity, y approaches 1. When x is 0, 0 divided by 2 is 0. 2 to the 0 is 1, plus 1 is 2. Okay. Let me, in order to do 25, let me introduce Euler's number, a new number that you haven't seen yet. I may have said something, but okay, so let's recall the following. I did actually give you a little introduction to this, like the first day of class, but so if I look at this symbol stands for a number. This symbol stands for a number. This symbol stands for a number. And also, so similarly, E stands for a number. Okay. It turns out to be an irrational number. You cannot write it as a ratio of two integers, also a transcendental number. Meaning it's not non-algebraic. It is not the solution, the root of any polynomial that just contains um, integer coefficients or rational coefficients. Okay, so the number e. Named after Leonhard Euler. It can be thought of several different ways. E is just the number found by adding 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3, 1 over 1 times 2 times 3 times 4, etc. So just keep adding up all those numbers. If you add up all those numbers, you get the number e. Similarly, I can think of e as the following. Take 1 plus the reciprocal of some number and raise it to the power of that number. Then, if I let x be very large, it will approach this number e. Similarly, if I take 1, add to it a number, and then raise it to the power 1 over x, then it approaches this number e as x gets very small. We can also think of it as, well, first let me give you the concept of the tangent line. So the tangent line to a curve at a point is the best linear approximation to that curve at that point. It can be thought of as, well, in many situations, it's the line that just touches the curve at the point. Okay. So let me look at if I see from above the graph of, let's say, 1 to the x would just look like this. The graph of 2 to the x looks something like this. Okay. The graph of, I don't know, 10 to the x will look something like this. And so what I notice here is if I look at the tangent lines for each of these, they seem to be going, let me get rid of, let's not put an arrow there, that'll confuse you. If I look at these tangent lines here at, well, x equaling 0, y equaling 1, then I notice that the slopes keep, have a slope here of 0, and then they keep going higher and higher. So it goes from a slope of 0 to bigger and bigger values. Okay. Well, eventually one of those values must be 1. And so let me draw this. This is the graph of y equaling, well, something to the x, where the slope of this tangent line so this is the tangent line at 0, 1, and suppose that this slope here is 1. Well, E is that base such that the graph, well, the slope of the tangent line at 0, 1 has a value of 1. So E is that base such that the tangent line to the graph y equaling e to the x has a slope of 1 when x is 0. Okay, so that is another concept that gives us the idea of what E is. It's that base such that the slope of the tangent line at 0 is 1. Another idea is what is E? Well, it's some number whose approximate value is 2.718 2818245 90452 35 36028, etc. If you actually look at it on your calculator, it probably looks like 7.182128182, and so it actually looks like it repeats, but it doesn't. It's just that on your calculator, what you can see are just the first few numbers. So it looks like it repeats, but it doesn't. It's a irrational number. It doesn't have any nice little pattern like that. Okay, so knowing this now, all we have to notice is that e here is greater than 1. So it looks like the sketch of it just looks like this. Let me do problem number 25. So let me sketch the graph of f of x equaling e to the 2x minus 2. So it just looks like the graph of e to the 2x, e to the x. And then we will compress the x-axis by a factor of 2, and then translate over by to the 2 units over. Okay, so let's look at this. So it looks something like, that's much too high. So it looks something like this. Graph of y equaling e to the 2x minus 2. So when x is 0, 2 times 0 is 0, and so this is e to the negative 2. And as x approaches negative infinity, y goes to 0. (27) f of x is equal to e the x minus 2 minus 2 Okay, so this looks like the graph of e to the x. We'll then translate this over 2 to the right and down 2. And so if I put my axes here, it should look like the graph of e to the x. So it looks something like this. So as y goes to negative infinity, as x goes to negative infinity, y approaches negative 2. When x is 0, y is e to the negative 2 minus 2. So that's this y-intercept. So that's the graph of y equaling e to the x minus 2 minus 2. Okay, so I have the following. It looks something like this. So at 0, it's 1. And at 1, it's 4. In exercises 29 through 32, find the value of b, if any, that would cause the graph of y equaling b to the x to look like the graph indicated. Okay, so this is y is equal to b to the x. Well, I have that y is 4 when x is 1, and so that says that b is equal to 4. So this is the graph of y equaling 4 to the x. Notice that 4 to the 0 is indeed equal to 1. 31. So my graph looks something like this. At 0, it's 1. And at 3, it's 8. Maybe I should also say 1 is equal to b to the 0, which implies b is not 0. Okay, so let's look here. So y is equal to b to the x. Similarly, we have 1 equals b to the 0. That just says b is not 0. That doesn't help us too much. But we also have 8 is equal to b cubed. Well, the cube root, so that says b is the cube root of 8. So b is 2. And so y is equal to 2 to the x. 33. Oh, that's it. So that finishes off section 13.1.